So yeah, I'm going to be talking about volcanic ash clouds. They are a serious, let's just get these videos going, serious issue in Alaska, and as you can see here, we're actually looking at some webcam imagery from Kamchatka. They're an issue across the whole of the North Pacific. And I'll be explaining how we use satellite data to detect these ash clouds, and then how we can actually predict those to provide warnings of the ash clouds. So you can see here, this is from June of 2007, a considerable volcanic eruption at Okmok Volcano in Kamchatka. And as Steve mentioned, in January of 2006, Augustine volcano erupted. This is webcam footage from the island itself across a couple of days at the end of the month. I was very fortunate. I landed December 9th, as Steve says. January 11th, the volcano started erupting. I was still learning how to live in Alaska. You can guess from my accent, I'm not originally from here. I was still learning to live in the middle of winter at 40 below, and I was getting information and having to come in at odd hours of the morning to work as part of the observatory. So it's definitely a learning experience of how to survive in Alaska. So in terms of ash clouds, what actually are they? There's sort of three terms that we have. There's volcanic cloud, which is any sort of airborne component of an eruption. And here we have two images of that volcano, Okmok again. These are from '94, where we have a satellite image. So this is using weather satellites that orbit around the Earth to be able to detect for those ash clouds. And the bottom left-hand image is a shuttle image of that same activity. Then we have a term, and you'll hear mentioned, what's called a plume. And that's what these are. They're still attached to the volcano. They haven't yet left detached from the volcano. And then there's an eruption cloud. And this basically means a volcanic cloud that could be either ash or sulfur dioxide. So for those that don't know, there's a lot of volcanoes across the North Pacific. This is a Google Earth snapshot, but it still shows, with these nice candy corn volcanoes, the number of volcanoes across the North Pacific, all the way from Kamchatka, here on the western side of the North Pacific region, all the way across the Aleutian Islands, through into the Cook Inlet region surrounding Anchorage. So potential activity at any of these volcanoes can be a serious factor for not just Alaska, but the whole of the region. Here's some of the examples of those volcanoes. Quite a few activity across the Russian continent. Some of those volcanoes across the Aleutian Islands and Alaska Peninsula. Mount Cleveland has been a fairly active volcano over the last few years. Veniaminov has had some steaming, and obviously Augustine. And then the volcano of interest at the moment, Mount Redoubt, close in next to Anchorage. So why do we want to actually look for and detect volcanic ash clouds, and why do we want to predict them? The North Pacific region is a big, what we call air corridor. Any air flight coming from the west coast of the United States, even from Chicago, even from the east coast, from New York, and coming down into Indonesia, into the Far East, will come across the Aleutian Islands. Because they will fly north, rather than flying west to east, they'll fly across Alaska for the shortest route. So there's a considerable amount of air traffic across the region. So the speed at which jets fly, then if a volcano erupts, you need to know where the ash cloud is as soon as possible to give them the warning that they need to be able to avoid those ash clouds. And also, if there has been an eruption occurring, what's the information that we can provide to then say, in the next 6 hours, where will the ash cloud be, so they can reroute aircraft, but still fly. So, a few people in the audience will remember the Redoubt eruption of 1989 to 1990. This started at the end of 1989. Ash clouds reaching 13.5 kilometers, 44,000 feet. So we're definitely up into the aviation routes. This is actually the famous cloud that you will see on the Alaska Volcano Observatory's logo. And this was actually from a pyroclastic flow rather than actually from a pure eruption cloud. There was obviously Mount Spurr, the Crater Peak region of Mount Spurr in 1992. 3 events across during that year provided and produced ashfall across Alaska, providing a fairly good covering across the Anchorage and Bowl region. Again, ash clouds reaching considerable altitude, reaching up to the aircraft routes. This here is a composite of satellite data. This ash cloud was not just confined to Alaska. It was tracked all the way to Greenland. It caused air traffic closures and affected air traffic in and around Cleveland, Ohio. So it was not just an Alaskan event. It was obviously of considerable interest and influence on Alaskan activities, but it still can affect the whole of the United States. And then, as Steve mentioned, Augustine 2006, we had 13 explosive events across a sort of 2 to 3 week period. Again, ash clouds reaching this 45,000 feet, 13 to 14 kilometer altitude. And you can see here, this is an animation of those ash clouds, of them tracking across the Cook Inlet and out into the Gulf of Alaska. And, as I said earlier, Cleveland Volcano. This was from 2006. This was actually a image taken from the International Space Station, one of our many observers that we have as part of the Volcano Observatory. This volcano is out in the middle of the Aleutian Islands. Due to its location, it's very hard to be able to install what we call seismic networks to allow us to look for any volcanic activity. So we have to use satellite imagery for this volcano. It's a very windy area, it's very hard to get to, and also it's impossible to get a good enough seismic network to be able to actually monitor the volcano. So for this eruption, we actually had a phone call at the AVO operations room in Anchorage from the space station to tell us that they'd seen an eruption occurring at Cleveland Volcano. Within about an hour, we had our most recent satellite data, and we were then able to see the eruption. So we tried to take as much information as we can, local observers and even astronauts on the space station. So, there's been a considerable amount of activity in Alaska and the North Pacific over the years, and I will show you some examples of 2 eruptions from 2008 later on. But what does an actual ash cloud consist of? Volcanic ash is generally the majority of the cloud, but there are other features to the cloud. Obviously with ash, it's just a mixture of sand, dust-sized particles, and obviously if you were in an aircraft you would not want to be flying through it. There's a lot of water in there, both in solid, liquid and vapor format. There's a lot of gases in there. SO2, sulfur dioxide, carbon dioxide and other volcanic gases, and simply air as well. Obviously it's the atmosphere. As a volcanic cloud disperses, these materials will separate further apart from themselves and the cloud will disperse. So although we call it a volcanic ash cloud, it may be made up of more than just volcanic ash. That's something to be wary of, that when you see an ash cloud, you're not just looking at the volcanic ash, there are other constituents in the cloud. Particle size. You can see that the particles themselves will vary. There will be very fine ash particles. As the volcano erupts, a lot of the larger particles will fall out quickly. As things settle in the atmosphere, the larger those particles are, the quicker they will fall out. So, generally, as the cloud disperses and is tracked across the atmosphere, the particles will become smaller and smaller and smaller. The larger particles will fall out, and as a result, it will come to a point when it's dispersed. Therefore, the particles are small enough that we're unable to detect them. So there's this region between the eruption itself at the volcano, where the large particles fall out, and eventually the cloud becoming dispersed enough that we can't actually detect it. And we're looking for that period within maybe the first 12 to 24 hours. where we can provide information on the location of the cloud and also its future movement to help the aviation community. One example where an aircraft was still stuck on the runway when there was an eruption. This is Mount Pinatubo out in the Philippines from 1991. And this is a US Navy photograph of this aircraft covered in a considerable amount of ash. And now there has been a lot more work done on assisting the aviation community to prevent events like this from occurring. Obviously, volcanic ash falling on the local airports can cause airport closures, with Anchorage Airport being one significant affected by eruptions within Alaska, both from Mount Spurr, Redoubt, and also Mount Augustine volcano produced some occurrences of activity at the airport because of the eruption. It can turn day into night. Living in Alaska, that's no different. We're normally expecting it to be the middle of day, but it's still dark outside, but not at 3 minutes to 1 in the afternoon, or 4 minutes to 1 in the afternoon. So this is daytime darkness caused by Mount Redoubt erupting in 1990. The ash will prevent the sun getting through, and it will actually cause nighttime during the day, even though a lot of us here are used to that during the middle of winter. So how do we, as part of the university and the observatory, work at monitoring the volcanic activity? The Alaska Volcano Observatory, that, for those that don't know about it, was created 20 years ago now, 21 years ago now, in 1988. And it sort of has three roles within its sort of day-to-day activity. Obviously, we're monitoring. We are actually detecting any activity, any unrest at a volcano, and monitoring to see if that volcano is going to erupt. We're also trying to research new ideas, new techniques. How can we improve our monitoring? How can we determine new activity at volcanoes? How can we test the boundaries of science? But also, and to me, one of the biggest parts of the observatory is education. We are here at the university, part of the observatory, and we're training the next generation of scientists. I've been through my degree process, through my degree teaching, whereas the next generation of scientists, the students, the undergraduates, the graduate students, this is one of the roles that the observatory can provide, is the next generation of scientists that can then go out and do the research and do the monitoring. Three main groups: geophysics, which sort of encompasses seismology and ground motion groups, geology, and then remote sensing, which is the sort of group I'm involved in as part of my research. Who is AVO and what is AVO made up of? There's three groups in the observatory. University of Alaska Fairbanks Geophysical Institute, that myself and Dr. Steve McNutt are members of. The Alaska Division for Geophysical and Geological Surveys, based here in Fairbanks. But also the USGS, the United States Geological Survey. So we have a university partner, a state partner, and a federal partner. And we have the USGS part of the observatory is based in Anchorage, and they are our federal head. They are the ones that deal directly with the National Weather Service, the US Environmental Protection Agency during any volcanic crises. And at the moment, with the unrest at Mount Redoubt, then our USGS partners are working very heavily with the local communities to work on reporting any change in the volcano's activity. Here at the university, we have a lot of students, therefore we're able to do a lot of the research into the background and new monitoring techniques. The monitoring itself is shared between both the United States Geological Survey and the two university and state group here. But a lot of the research can be done here at the university because of the number of students we have, and students are very good at doing research 24 hours a day. The Alaska Volcano Observatory obviously deals with volcanic eruptions, but worldwide there are what we call advisory centers. And these are centers that provide the warnings to the aviation community about impending eruptions. They work very closely with the local volcano observatories. We have an advisory center, so this is called the Volcanic Ash Advisory Center. One of the things about the National Weather Service is they do like their acronyms. There's one of them based here in Anchorage, in Alaska. And you can see here, there's numerous sites worldwide, and the area that you're seeing here is the area that these advisory centers are responsible for. So, for example, in Anchorage, it's responsible for the volcanoes across Alaska and into the Aleutian Islands. There's a Volcanic Ash Advisory Center based in Washington, D.C., and that deals with any volcanic eruptions within Lower 48, Central and Northern South America. So during a volcanic eruption or volcanic crisis, this advisory center will be talking directly to the National Weather Service within each country. Obviously here we have National Weather Service in the same country as the Volcanic Ash Advisory Center, but also the other volcano observatories. So here in Alaska, we are lucky that we have the advisory center, the volcano observatory, and the National Weather Service all within the same city. Issues can occur when the Washington Advisory Center has to make a release on information about an eruption in Central America. And these advisory centers will be the ones that will deal directly with the aviation authorities. These advisory centers themselves have been around probably now for 10 to 15 years. They weren't in place when Mount Redoubt erupted. The International Civil Aviation Authority has dealt very heavily with volcanic ash. Pilots are now have training on how to deal with volcanic ash episodes. They have these advisory centers. They have working groups dealing with the issues that can occur from a volcanic eruption. So there's lots and lots of different groups now dealing with volcanic eruptions and also volcanic ash clouds. So we're all working together. We're all using all of our skills to provide as much information as possible on the volcanic ash clouds and the volcanic eruptions to therefore provide the best warning to the public. So in Alaska, the Weather Service and the FAA will work together. There's another weather unit based in Anchorage that will also deal with volcanic ash clouds. So within Alaska, we are very fortunate here, the number of different units that are involved. And you may look at this and go, well, why have we got 6 different groups working on volcanic ash clouds? We have the Alaska Volcano Observatory, and this will deal with looking and trying to predict when a volcanic eruption is going to occur. Then when a volcanic eruption has occurred, obviously the ash clouds will then be up into the atmosphere. So one of the deals is that we have to deal with the National Weather Service to provide the official warnings with the advisory centers. These advisory centers, as I spoke about, although they are national and although there are 9 of them worldwide, they are actually maintained by the local weather service. So although I talk about the National Weather Service working with the observatory, it's these advisory centers working with the observatory. So here in Alaska, we have the National Weather Service are actually the ones that maintain the advisory center. So that's sort of a brief overview of sort of the different groups that work in terms of providing the warnings and monitoring the volcanoes. Here at the university, we have the remote sensing group, and we're using satellite data to look for and detect for volcanic ash clouds. So we have, for those that have not been up to the Geophysical Institute, a number of satellite dishes on our roof. This one on the right-hand side here is actually the synthetic aperture radar dish. But we have dishes that locally collect satellite data. And we are using the same satellites that you will see when you watch the local weather. These are satellites that have been collecting data for over 30 years. They're just standard weather satellites. And when you see a weather satellite image, you'll either be looking at what we call a visible image. So therefore, if you yourself were looking at the Earth from the satellite itself, or what we call the infrared part of the radiation. And we, as part of the observatory, divide up the region to look for volcanic activity. So we're not looking for any thermal signals, any new volcanoes occurring out in the middle of the Bering Sea. So to speed up our analysis, so this is all being done with computing systems, we divide up the region to speed up our monitoring and detection. So the names of these regions generally are given by a volcano that's within the center of that region. We have recently, within our group, started to put together some online tools. The data that we collect comes from the local receiving station and also from our colleagues at the NOAA, at the National Oceanographic and Atmospheric Administration. But to make it easier for ourselves to analyze this data for ash clouds and to be able to provide the reports the observatory releases, we have some online tools. And later on I have a slide with links to all of these. If anybody's interested in some of these links, then please see me afterwards and I can give you a copy of that slide. Some of these links are password protected just to allow us to have some internal discussions on what's going on within the observatory before any official information releases are provided. But we have links to the dispersion model, information on any thermal activity at our volcanoes. And one of the links of interest is what we call our data center. These are links to all the different satellite images that we collect and analyze within a day. There are many different satellites that we use for tracking ash clouds. This one here is one of the National Oceanographic Atmospheric Administration satellites. And we have quite a few satellite passes a day. When I talk about a satellite pass, this is a satellite that is orbiting the Earth in a polar orbit, so it's circling, coming across the polar regions, and as it tracks across the region, the satellite receiving station will detect the satellite on the horizon. As the satellite passes over the region, it will track the satellite, and once it leaves the horizon, it will lose what we call lock with the satellite, and it will wait for the next pass, collecting data as the satellite comes over. And as you can see, over a 24-hour period, we have a considerable amount of data. This one here, what we call GOES, this is your standard geostationary. It sits on the equator. And this is what you will see when you see a weather satellite. When you're looking at a weather image on the news, you're seeing an image that covers the whole of the North Pacific. That's what this is. It's a satellite that sits stationary on the equator, and every 30 minutes it takes a snapshot of the whole North Pacific. So we're able to use this data for ash clouds as well. So we have a lot of data that comes in 24 hours a day that we use to search for ash clouds. So this is one of our online tools. I'm showing this animation for the region around Redoubt Volcano. And anybody can look at this. This is publicly accessible, and it allows you to see the satellite data in the different signals that we are locally receiving. You can select one of our different regions, and then, as you can see, with time, you can actually animate and see any activity occurring at the volcanoes. However, how do we use satellite data? So you're thinking that we're using weather satellites. How do we actually use a weather satellite? Right. This is actually an image from 1992 from Mount Spurr's eruption, and there is an ash cloud in that image. This is your normal image that you would expect to see from a weather satellite that you would use to look at the weather if you were watching the news. This is a single band, this is a single channel in the system. However, if we take two of the channels and difference them, there's your ash cloud. So this is your normal weather satellite, and then conveniently two of the channels, so the data that comes from a satellite is not just in the visible. There's many different channels. It's looking at different parts of the energy coming from the Earth's surface. Taking just a simple difference, we're able to detect ash clouds. So we use this very simple differencing technique to be able to detect for an ash cloud. We also have regions centered on the volcanoes to search for any thermal activity. Again, this tool is publicly available and can be viewed by anybody that's interested in looking at the activity. It can actually be used for class projects. It can be used for students. Some of this information can be downloaded and can be used in class projects. We use it as part of our university graduate class and could very easily be used in a high school class project as well. So as you saw from 2 slides ago, we are able to use a very simple difference to determine where an ash cloud is. However, that image does not come in instantaneously. We don't get it as soon as the satellite comes over. There's a 20-minute delay. It takes time to process the data. We don't know where it's going to be in 6 hours. How's that ash cloud going to move? So we need to be able to predict where the ash cloud will go. So to do that, what we call model the ash cloud. We simply predict its location 1 hour, 6 hours, 12 hours into the future. So as we say, there's been a reported eruption. First thing to say is, where is the ash cloud going to go? Where is it going to track? We may not actually get an observation. We may not get a pilot report, a ground observation, a satellite image. So the first thing we want to do is we want to say, what are we going to provide as our warning where the ash cloud is going to go? So we use computer models. We take a model and we release into the model on the computers ash particles, and then we track where they will go based on the local wind fields. What's the model that we use as part of the university and the Volcano Observatory? Well, it's simply the PUF model. This model has been around for probably nearly 20 years. It's been developed by many scientists within the university, being headed by Professor Ken Dean at the university. And sort of information that we put into the model are things like, how high is the ash cloud? So we tell the system that the ash cloud is from the top of the volcano to 10 kilometers. What time from seismic information, from other data, did the eruption start? Generally, with a lot of volcanoes in Alaska, we may know that start time because we have seismic information. The eruption length. Obviously, this is very difficult if the volcano is continually erupting. So what we may do is we may put it in a set length. How do we want to define the plume? As we saw for those photographs early on from Mount Redoubt from 1989, we would want to put a lot of the ash throughout the whole atmosphere, from the ground all the way up to the top. And then we would want to then predict where this ash cloud will go. So we have an online website for this. If a volcano erupts, and has done, the day after Christmas, at 2 o'clock in the morning, you don't want to have an analyst get up, get dressed, go outside at -40, come into the observatory and set up the prediction. I can tell you it's not fun. So, I've set up, through our website, automated predictions. So these are volcanoes across the region that have had some activity in the last 3 years. And it will then automatically, every 3 hours, provide a new prediction. So, if a volcano has changed its unrest, for example, Mount Redoubt, which is now at an orange color code, then when it reaches its yellow color code, it will be added to the automated list. So if the volcano then does erupt, and there are reports of volcanic activity, without actually having to set up the model run, whoever is on 24-hour operations within the Weather Service or within the Advisory Center can go to this website and look at the prediction straight away without having to assume the height of the cloud, to assume how long it's going to erupt for, to put the information into the actual model itself. These predictions allow you to quickly get an idea of where the ash cloud is going to go. So this is an example from Kasatochi volcano in 2008, and here we can see the movement of the cloud color-coded by altitude, with the purple color being low level and the green being high level. And then we also have, through our website, the ability to actually run our forecast. So when we have more information and we're able to get people to be able to get information on heights or eruption lengths, we can then get a more accurate prediction. So these automated predictions are our first information on the hazard and the location of where the ash cloud will go in the future. Therefore, we can provide warnings within minutes of the location of the ash cloud. A new sort of tool that I've been working on is, we've all used, and the majority of us have probably used and heard of Google Earth. Google Earth is a software that you can use for searching anything on the Earth. A lot of us will use it to probably go and find out where we used to live or the distance from certain places to where we live now. But I've been able to use Google Earth to actually display the prediction. So you were looking at, here we have a prediction where we're color coding by altitude. This is actually a different eruption, but you can actually see that the movement and the shape of the ash cloud in a three-dimensional view. Something that is very useful when you're trying to understand the prediction that you're generating. So in 2008, we had some considerable activity across the Alaska region. Obviously, Redoubt is now at unrest and is a volcano that we are currently watching 24/7. But 3 volcanoes provided some interest, I should say, for us in 2008. And I'll talk today about Kasatochi and Okmok, because these were the larger of the activity. So Okmok Volcano erupted in July 2008. On the 13th of July, this is a satellite image, visible, so obviously as if we were actually sat on the satellite. We can see, here's the steaming, the white cloud, and then a lower level ash. This is a photograph taken from an aircraft going over the region. As you can see, a fairly considerable eruption. I'll let this play and then I'll talk about it. What you're hearing in the background is the seismic signal from the 2 closest seismic stations. This has been very kindly lent to me by Celso Reyes, one of our PhD students, and he's taken the seismic signal to the west and the east of the volcano and tuned them into the left and right speaker. In the background, this is a satellite image, so this is what you would normally be looking at when you're looking at a weather cloud. And you can see here from the eruption of Okmok, the ash cloud, or a lot of steam to start with, some lower level ash, and then as the eruption continues, it's producing an ash cloud up to sort of 60,000, 50,000 feet. The eruption itself produced not just ash, it produced a considerable amount of sulfur dioxide. This is an image provided to me by another British colleague of mine, Fred Prada. This is the tracking of the sulfur dioxide from that volcanic eruption during 2008. So again, producing both ash and sulfur dioxide. So the other eruption from 2008 was Kasatochi Volcano, Kasatochi Island. I'll play the sound in a second. This is going to be again from Celso using the closest two seismic stations, and when I actually play it, I'll have to stop talking because it is fairly loud. So that again was the seismic signal from the eruption, and in the background is the satellite image collected locally here in Fairbanks, even though it's an Aleutian Island eruption. So this is actually just visible data, so you can see the weather clouds are white, and then we see the eruption itself occurring. This was produced ash up to 50,000 feet. Again, disrupting air traffic. After the eruption itself, it produced nearly 400 meters to the shoreline through deposits. Again, you can actually see that it's producing some form of steaming, even at this, from this image. Local communities were affected, ashfall occurring in the surrounding communities. This is a fairly comprehensive image. But this is what we call a composite. So this is all of the images added together. So this was not occurring at one time. This is as the ash cloud moved across the region, we added together all of the satellite images to show the extent of the ash from this eruption. So we can see here the location of the volcano and the actual ash itself tracked for several days across the North Pacific for about 1,500 to 2,000 kilometers. So a very considerable eruption producing a large amount of volcanic ash. And here's an animation of that provided to me by another one of our students, Joe Lovick. So here you can see the eruption, the ash being caught in the local weather system. It stopped erupting actually at the volcano in terms of the amount of ash, but you're still able to track the ash across into the North Pacific. And eventually the ash itself gets to a level that we can't detect it in the satellite data. However, an issue occurs. This is the sulfur dioxide from that same eruption. As you can see, this is an image provided to me by Dave Schneider at the USGS part of the observatory. This sulfur dioxide cloud was tracked 3 times around the globe. When this volcano erupted, as I said, the ash reached 50,000 feet. The sulfur dioxide cloud probably reached higher. And in the atmosphere, there is 2 different layers. What we call the troposphere, which is what we live in, and then what they call the stratosphere, which is above 10 to 15 kilometers and higher. If, as with this eruption, the sulfur dioxide part of the eruption reached into that higher part of the atmosphere, then it's hard for that sulfur dioxide to settle. The ash will stay in what we call the troposphere, this area that we live in, and therefore it will settle out eventually. With this sulfur dioxide, it reached this higher level in the atmosphere. This also happened for Mount Pinatubo, which was an eruption in Indonesia, and that's why the sulfur dioxide was able to track around the globe, because it reached this higher level of the atmosphere and was trapped. It couldn't settle back down into our lower level of the atmosphere, and therefore it was tracked around the globe. So those are 2 examples of eruptions from 2008. Now briefly, Redoubt 2009. We have a lot of monitoring systems available to us for this eruption, or this, I should say, not eruption, this unrest. It's not erupting yet. This unrest. We have a lot of seismometers available to us. We have satellite data, which will allow us to look for volcanic plumes and ash clouds, and also any thermal activity from the ground. We are working with our colleagues at the Weather Service to use their local radar, which allows us to look for volcanic ash as well. We can actually use GPS stations to look for ground deformation. We have observers and also gas flights occurring on a fairly regular basis. We have a couple of webcams that are pointed towards the volcano, and you can view these through AVO's website. We also have some lightning detectors along the Kenai Peninsula through collaborations with colleagues of Steve McNutt's at New Mexico Tech. We also have some aerosol samplers, and we're also working with the United States Fish and Wildlife Service to get out more of these to be able to, if there is an impending eruption, to detect the volcanic ashfall. So for those that are interested, what's happening at Redoubt? Well, the rest is continuing. As of Monday, there was a small steam plume coming from the summit crater. There was some volcanic tremor, occasional discrete earthquakes, and sort of the feeling is that new magma is likely to be sort of more than 5 kilometers below the surface, with a possible small amount rising to lower levels. You can read about the ongoing activity at Redoubt from the AVO website, so please go there and read that. We are running scenarios of potential eruption clouds for any impending eruption using our dispersion models. We're looking at possible any potential ashfall, predicting what the ashfall may be if the volcano erupts. And I guess the main thing to state is that AVO continues to monitor. We're staffed 24 hours a day, 7 days a week, 365 days a year at the moment. Hopefully it won't last 365 days, the continued unrest. But we're monitoring it, we're looking using all data available to us to provide any warnings that would be required for the eruption, for any impending eruption. Just to finish off, a couple more slides, and then I'll be done. What you're looking at now is the model that we use for forecasting can also be used to look at past events. The model very simply uses wind fields that you would normally use to predict the weather. And what we're looking at here is, this is an animation and goes on for 12 minutes, but I won't play all of it. But we use the model to analyze past events, to look at past eruptions. And I've put together this animation of all the volcanic eruptions in the last 38 years in the North Pacific region, putting in obviously any aircraft encounters, any airports that were affected, starting at Karimsky eruptions in 1970, going all the way through to the recent eruptions of Okmok and Kasatauchi of this year. And this animation is available through the model itself's website. What I will show next is, this is a composite again, showing the location of the ash clouds for the last 20 years. So this is actually the 20 years of the observatory, where those ash clouds reached 12 hours after the eruption started. So you can see basically the whole of the North Pacific is affected and has been affected at some time because of volcanic eruptions. So for an ash cloud to reach 20,000 feet, so that's about 6 kilometers altitude above sea level. So this is obviously getting into the aviation routes. 230 separate events in 20 years. 11 and a half a year. So pretty close to one a month for 20 years. So it's not just an effect that occurs on an infrequent basis. It can occur considerably over the year. Next, I'm going to show a animation after the link slide of the actual Redoubt encounter, and you're going to hear the audio from the cockpit, but also how we've been able to use Google Earth to better understand the encounter and how long the actual aircraft was in the ash cloud. As I say, here's some links that may be of interest, and I'll be happy to provide a copy of that slide later. You'll see the plane coming in here.
We have to go off now. It's smoky in the cockpit at the moment, sir. Kilo 867 Heavy, roger, left is your discretion. Yeah, we fly out 6 miles in black cloud, and the heading is 130. 167, we have before out oasis, and we are descending now. Kilo 867 Heavy, anchorage. Kilo 867 Heavy, we are descending now, we are in the fall. Kilo 867, we go over your signals you have, sir. Give us your effective, please.
So this was a encounter from that 1989 eruption of Redoubt, where a Dutch KLM jet flying into Anchorage en route from Amsterdam to Tokyo encountered the ash cloud. Since this event, there's been a considerable amount of work done. This was before the advisory centres were around. This was only a year after AVO was founded. The jet knew that there was an ash cloud in close proximity. There was warnings out there, and it basically was flying towards Anchorage Airport, detected ash in the cockpit, and at the time, the protocol was to treat it like a weather cloud, which was basically to rev its engines and try and lift over it. However, when you rev your engines when there's ash in the air, that's not the thing to do. That's now not the practice. It's completely changed. The aviation's understanding of volcanic ash is completely zero tolerance, that they will go nowhere near an ash cloud. They are completely aware of it. They're training their pilots. They have official documentations out there that are ratified by the Civil Aviation Organization. When Mount St. Helens was at elevated alert, KLM flights were even worried about flying into Seattle Airport. They have a very zero tolerance for volcanic ash. With this encounter, thankfully, everybody survived. But it showed that within minutes of encountering an ash cloud, how the aircraft could very easily be affected. Now the protocol has changed dramatically. But this aircraft, $80 million worth of damage. The pilot is still in pilot today, and the aircraft is also still working today. However, now the protocol has completely changed. They will avoid at all costs. If they are coming into an area where there's a predicted warning, they will divert, they will turn around, they will bank and go where they were, where there's no ash cloud. Now there is these advisory centres out there. The volcano observatories deal a lot closer with the local weather service now. The aviation authorities in each country has ratified agreements with these advisory centres to provide these warnings. And there's now official releases that go out about any volcanic activity. So these sort of events are now very infrequent, and there has not been any for a few years. And finally, the work I have been doing has sort of got a bit of press. This is a Popular Science article from sort of 2008. I'm putting this up just to let people know that sort of, I guess, what the sort of media can do. This is the KLM jet that was in my little Google Earth animation with the logo removed, stuck over a Russian volcano. But they wanted sensationalism to show what we can do with Google Earth, but it's just to show that although we are sort of doing a lot of research and everything, there is a lot of interest in what we can provide to help mitigate any impending hazards. And with the observatory, the university, the Geophysical Institute, and these advisory centres, it's safe to fly. And I can tell you because in 2 days' time I'm flying to England. So I'm hoping that there will be no impending eruption at Redoubt between now and then. But as I say, having worked directly with the advisory centres, being there when there's been activity, they're completely on top of it, 24 hours a day, 7 days a week. And these sort of events like the KLM event are now very, very infrequent. And I've been to these official meetings of the Civil Aviation Authority and the local weather service and these volcano watch programs, and they're on top of it. It's a big hazard. Volcanic ash clouds can produce large eruptions and can impact the aircraft routes. But there are lots of groups out there working very hard to provide all the warnings that are required to prevent events like the KLM encounter. Thank you.